Hi everybody, final product video. Next I'll go on to the project videos where we'll start really tinkering with the board. This video will talk about the 555 timer circuit in monostable mode, the PIR passive infrared motion detector attachment, the infrared sensor, and the thermistor attachment. We'll go into some detail about the theory behind it. I'll give you an example or two. We'll talk about the pin block pins, and I'm sure there will be other things that I want to fit in there before the end of the video. I know it's long. I sincerely appreciate your patience. If you are one of the people who have pledged for my Kickstarter, you will find a lot of value in these videos, and if you are interested in this board, possibly to purchase down the road, I'm sure you'll find it useful. All of the schematics, all of this stuff will be documented in the upcoming manual that will be done by the end of this month. So let's get started. This is the 555 timer integrated circuit, IC. It's got 8 pins. These are the surrounding components. We've added some customization here. The 555 timer is a very versatile chip. It can be used for many different things, namely for as a frequency generator. But we're actually using it in monostable mode, which means that once it's activated, it creates a pulse width that is determined by us. And we'll be testing this with our onboard LED. Anyhow, there are 8 pins. There's an indicator on the left-hand side, a little notch, that indicates the left side of the chip. This is pin 1, pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, pin 8. We're not using pin 5, but we're using all of the other pins. Pin 1 is the ground pin, which is connected to our common ground line. And pin 8 is our VCC pin, our power supply pin. So when ground is connected to pin 1, 5 volts is connected to pin 8, the circuit is operational, it's powered. And we've got that obviously connected to the 5 volt line. We've got a bunch of stuff connected to the 5 volt line here. Let's talk about pin 4. Pin 4 is the reset pin. If that pin is held to 5 volts, or the equivalent of VCC, whichever is on pin 8, then the 555 timer will be activated. This is an optional pin to use. Usually you tie it just straight to 5 volts, but what we're doing here is we've actually got a power on reset circuit. We've got a 10K resistor connected to the 5 volt line in series with a 10 microfarad electrolytic capacitor. So what happens is as soon as power is applied to the circuit, the 5 volt supply charges this capacitor. So think of it as a cup being filled up at a tap, but it's being limited by how much current can actually fill that glass by this 10K ohm resistor. So what we get here is basically a time period in which the chip is inactive. Once the charge imagine that this is a cup, reaches a certain threshold close to 5 volts, then the circuit will become active. Now what we're actually using this for is basically when we plug in our multi-sensory electronic learning board, we want to make sure that the output isn't triggered by the power on. And so this basically allows for us to power on, and we'll have a short duration in which the chip will be inactive. Once the charge on the capacitor, after a little short period of time, reaches the threshold close to 5 volts, then the chip will become active and our output will not be falsely triggered. So again, imagine this as a cup. Imagine this as a filter only allowing a certain amount of water to fill up that cup. And that's this right here. Now ignore this formula for just 1 second. Ignore this table for just 1 second. In order to generate a pulse width, what we need to do is we need to use a similar circuit, filling up a cup and limiting how much current, or how much water, rather, in this case, we're just going to use water and a cup as an explanation. We're going to use the last variable resistor on the board, labeled DLY. It's a 3-pin variable resistor or potentiometer, so we can make the delay really, really long, or semi-long, or really, really short. There's a 220 microfarad electrolytic capacitor in series with this potentiometer, variable resistor. So by tuning this with a small flat-edge screwdriver, we can change the delay. The 220 microfarad electrolytic capacitor is fixed. So in order to determine, for most of our projects, we'll just be using an LED indicator to calibrate how long our output pulses are. But if you wanted to make your own specialized pulse and with a very specific delay, how you determine that is that you would put between 5 volts, a fixed resistor that you'd use the following calculation for, and a fixed capacitor. And that essentially creates the equivalent to this. Now, the time for the pulse width is based on this calculation. 1.1 times R times C. So 1.1 times whatever value you have for this resistor times whatever value you have for this capacitor. Now, we've got a variable resistor here, so it can be many different times. So just for an example, I've placed, let's say this is a 10k ohm resistor. Let's say we've got this tuned to 10,000 ohms, 10k, 10,000 ohms. We would multiply 1.1 times 10,000 times 0.00022, because 220 microfarads is the equivalent of 0.000220. And if we do that calculation, we get a pulse delay of 2.42 seconds. And so basically when our output is triggered, say it's triggered right here, this pulse width will go from 0 to 5 volts, stay high, and then fall. And the pulse width will be 2.42 seconds. Now, resistors and capacitors have tolerances, which means they're not perfectly accurate. If you get a 220 microfarad capacitor and a 10k ohm resistor, resistors typically have, you can get lower tolerance resistors, but your typical resistor is going to have a 5% tolerance, which means it can be 5% accurate, within 5% accuracy, essentially. It can be 5% more than 10k, it can be 5% less than 10k. And same with the capacitor, except for the capacitors typically have a tolerance of about 10%. So basically you can get a value of 220 micro plus 5%, or in worst case, or 220 microfarad minus 5%, opposite worst case. Anyhow, you're not going to have to worry about that. You usually wouldn't use an RC resistive capacitive circuit to do such a thing anyway. If you were trying to get a very, very, very specific time delay, you'd use a microcontroller. But anyhow, I digress. I'm rambling on. We'll do one more example of this in a second, but let's talk about the rest of the circuit. So pins 6 and 7 are actually connected together, and we've got those two pins also connected between the resistor and the capacitor. So basically this is sensing how much voltage is on the capacitor as time progresses. So as soon as you activate it, the output will go high, and it'll stay high, and then fall low after the time duration has elapsed. Hopefully that makes sense. So make sure that if you're going to make your own 555 timer circuit, you connect pins 6 and 7 together, and then connect those two pins between the capacitor and ground, or between the capacitor and the resistor. Of course, the other side of the resistor is connected to our supply line, VCC, 5 volts, and the negative side of the electrolytic capacitor is connected to ground. So you activate it, the capacitor fills up, and the output drops. That is your pulse width. Anyhow, let's talk about the trigger circuitry. We're not using pin 5. We've supplied 5 volts to our supply line on pin 8, ground to pin 1. We'll talk about pin 3 in a second, because that's the last thing we want to talk about. We want to talk about how do we trigger this. Well, there's two ways of triggering this, based on the circuit on the board. There's a manual trigger, the DLY button, the only button on the board. This is for calibration. So you tune your delay using the DLY potentiometer, variable resistor. You press the button, you connect the output to the LED, and the LED will turn on for however long the pulse width is set for, and then it will turn off. Now, that is the manual. This is for calibration. Very, very, very easy to use on the board. But say we want to use the output of an amplifier or a sensor to activate it under a certain condition. Say for a laser circuit or a vibration circuit. We're going to use the in pin. The in pin is on the main sensor pin block, And what that is, what's happening there is that's connected to a 1 k ohm protective resistor that's fed to the base of a transistor. Now, transistors are used for many, many things, but we're using it essentially as a switch. As you can see, pin 2, that's our trigger pin, is connected to a 10 k ohm resistor to our 5 volt line. So what that 10 k ohm resistor is doing, it's acting to protect the circuit from shorting, because if I have 5 volts and I don't have that resistor there, and I press this button, it's going to connect 5 volts directly to ground, which is a short circuit. It could potentially harm our regulator, it could hurt our power supply, it can hurt our circuit. So this is limiting current, so that we press that button and it's harmless. It just consumes a tiny bit of power, a very tiny bit of power. But this is, again, our secondary. When that's pulled low, when we see 0 volts in this line, it triggers the operation. So by default, there is 5 volts on pin 2 through that pull-up resistor. We press the DLY button, short that to ground. We still see 5 volts here, but we'll see 0 volts here when we press that button. Now, the other way to do it is the transistor switch. We've got the, you might notice that the transistor here has 3 pins, a collector, a base, and an emitter. And this is an NPN transistor, which means that when a positive pulse hits the base through this protective resistor, this will act to sync the signal from the collector through the transistor to the emitter, which is connected to ground, which will short the line there. But it's a good short, it's a protected short. Hopefully that makes sense. I know I'm talking about a lot of things all at once here. If I am confusing you, try to watch it again, this segment anyway. Anyhow, so whenever we place a 5 volt signal on the in pin, we've got our 10 k ohm protective resistor protecting the base, but what will happen is that this signal will tell the transistor to sync whatever power on the collector is through to the emitter, which will bring the 5 volts on pin 2 to ground, and it'll activate our operation. That will trigger the pulse going high. Now, this 10 k ohm resistor is probably the most unnecessary component on the board. It's there as a bleeder resistor. It's just in case whatever's connected to the in pin is malfunctioning and offering a variable voltage. This just acts to bleed off any extra current there, so we don't get any accidental triggers of the 555 timer in monostable mode. So we've got our software, or our sensor trigger on the in pin. We've got our calibration button that does the same thing as this circuit, but it's a manual press to calibrate. We've got our power on reset circuit that allows for us to power on our board and not have a false trigger of the operation on power on. And we've got our timing resistor capacitor network here that determines our pulse width. Now, our DLY output. Now, I've already labeled the potentiometer here DLY, but our output on the main sensor block, on the pin block, is labeled DLY. So that's where we're going to actually see this pulse width. So when we want to see what that pulse width looks like, we would connect that to an LED just for calibration purposes. The in pin and the DLY pin is on the main sensor pin block. So let me show you that now. Our onboard LED circuit is right here. It's very simple. There are 2 components: a 470 ohm current limiting resistor and the 3mm red LED. Now, if we connect, say, 5 volts to our LED line, we don't have that current limiting resistor, then what's going to happen is that LED is basically going to take as much power as it can, and the LED will burn out almost immediately. So we need a solid 470 ohms to limit current to the LED. Now, the LED has a positive side and a negative side. The positive side is called the anode. The negative side is called the cathode. We connect the negative side, the cathode, to ground, and we connect the signal path to the positive side, or anode. You might notice the 2 little lightning bolts. I call them the lightning bolts here. That's an indicator to show you that it's an LED, not just a standard diode. LED does stand for light emitting diode. So this pin right here is not on any of the pin blocks. It's isolated. I'll show you where it is in just a minute. So if we want to do run a calibration on any circuit on the board, in this case, say our 555 timer, we use a female-to-female connector to connect the DLY output to the LED pin. And then we can see how long our pulse widths are. What I've got here is the DLY output on the main pin block connected to the LED pin. The LED is actually right there. Now, if I didn't have the power on reset circuit on pin 4, this would likely cause a false trigger. No false trigger, the LED didn't go on. So I'm going to press the DLY button. Very short delay. Now, what if I turn the DLY variable resistor right here clockwise a couple turns? You'll notice that the delay is longer. It's going from 0 to 5 volts for a longer period. So let me keep turning it. Oh, the pulse is even longer. Let's turn it a bunch more times. There we go. So we can make it long. Here's a challenge. What's 1.1 times 50K times 220 microfarads? That is the full duration that you can adjust to using this monostable multivibrator circuit.
The LED pin and the LED just above it are circled on the upper left. The DLY variable resistor, labeled DLY 50K, is just to the lower right of the LED pin. On the bottom you'll see the SEL, or rather DLY button, and that is actually going to be used for the calibration of our 555 timer, as we just talked about. The in pin and the DLY pin are on the main pin block highlighted in red.
Finally, something a bit easier, the infrared sensor. Now, when the board is powered, if you take your remote control for your TV and you point it at the sensor itself, the VS1838B, then what will happen is you'll see what your TV sees when you point your when it's actually receiving a signal from the infrared LEDs on your controller. Now, if you saw the Kickstarter video, you'll actually see a scope plot of what you'll see at the output, and I'll be showing it to you again when we talk about it during the project videos. This is still the product videos, so I'm just trying to explain all of the schematics. It's a very simple sensor. What it does is it takes that infrared signal from your controller, amplifies it, and gives you a square wave output, so between 0 and 5 volts. So I've labeled the pins. This is the sensor front, pins 1, 2, and 3. Pin 1 is your output, pin 2 is connected to ground, pin 3 is your VCC, power supply pin, which is connected to 5 volts. Now, to protect the inside of the VS1838B, we add in a 10K ohm resistor. Because what happens is say I overload the output, there's no current limiting through the internal circuitry of the sensor, and it could potentially burn out the VS1838B. So I've added in a 10K ohm resistor for that, and so we've added a 5 volt supply, current limited, to pin 3. Our pin 2 is grounded to common ground, and pin 1 is connected to the main pin block, the IR pin.
On the upper left, the IR sensor is circled in red. On the lower right, the output of the IR sensor is labeled on the main pin block, labeled IR.
Another simple circuit. This is the PIR passive infrared pin block. We'll be using female-to-female connectors to connect this pin block to our external PIR sensor module, passive infrared motion detector module. And what that will do is it'll pick up on movement based on detecting the infrared spectrum given off by the human body. In any case, there are 3 pins. The sensor pin block on the lower left is labeled PIR. The 3 pins are labeled VCC, SIG, and ground. SIG means signal, VCC means supply, 5 volt supply, ground means common ground. So we've obviously got our 5 volt supply connected to VCC internally on the board, ground connected to our ground pin, and the SIG line is connected to the main pin block to the pin labeled PIR, so we can use that output for something else. So when the time comes, I'll actually be showing you how to manually connect your PIR sensor to the sensor electronic learning board. It's very easy to do, but again, we're just trying to show you the schematics for a basic understanding of how these interfaces are actually being powered and talked to.
The PIR pin block is circled in red right now. You'll notice on the left it's labeled PIR, and on the right the three signal lines are labeled from the top down: GND for ground, SIG for signal, and 5V for 5 volts. That's our supply line, our VCC. And the signal line is fed internally to the PIR pin on the main pin block that is circled in red.
This is the thermistor attachment circuit. There's a 2-pin header on the board labeled Therm, T-H-E-R-M, and the circuit on the board in green is a 5-volt or VCC connected to a 10k ohm resistor to the THRM line on the V2.0 board main pin block. I'll show you that in just a minute. When you clip on the external thermistor to the 2-pin header, what you get is this, essentially a variable resistor. But the resistor, it's not variable, it's variable in the sense that the resistance of the thermistor changes based on the temperature. So what we've got here is a voltage divider. 5 volts, 10k, to a variable thermistor resistor to ground. And I'm going to show you the circuit equivalent in a second. And I'm also going to show you, it'll be included in the manual, but I'll show you in just a minute, the different values based on temperature for this thermistor. So what we'll get here on the therm line is based on the temperature, we'll get a variable voltage between this resistor and this resistor. And that variable voltage can tell your microcontroller what temperature it is. And it's pretty accurate too. So let's talk about the circuit equivalent. Let's talk about voltage dividers. This is the circuit equivalent. We've got our 10k fixed resistor tied to the 5-volt line, and we've got our thermistor tied in series with the 10k ohm resistor. The secondary side of the thermistor is connected to ground. So we've got in the middle our divider voltage will always be different depending on what the temperature is. This stays always at 10k. This changes based on temperature. So the data sheet just says that at 20 degrees Celsius, the resistance of the thermistor is 12.5 k ohms. So to determine what our voltage at the thermistor line will be, we need to use this formula. Now, before we get into the formula, let's look at this as RA, and let's look at this as RB. We need our VCC, which is our power supply, 5 volts, divided by our total, so RA plus RB, and in this case our R total is 10k plus 12.5k, which is 22.5 k ohms. Once we have that value, we multiply it by the value of RB, which is 12.5 k ohms, and that will be the voltage at our therm line. So basically you can feed this line to a microcontroller and you can write an algorithm to say what temperature it is based on the voltage here. You can use an analog to digital converter. Most new age microcontrollers have it. Atmel certainly does. PIC does. In any case, so let's plug in the values again. 10k or 5 volts, 22.5 k ohms times 12.5 k ohms. Pause it for a second and let's see if we get the same answer. .777 volts. Now on my calculator I get 2.777 repeating. That symbol over top means repeating. So 2.77 volts. If you want to round, since it's 2.777, you can round to 2.78 volts. If I were a teacher, I would suggest that is okay on a test. In any case, so that's how you determine in advance if you're designing your own circuit. If you have a specific thermistor, you have a fixed resistor, this is how you can communicate with your microcontroller. You put that into your design, and that is what you would get for 20 degrees Celsius. So let's look at the pin block, let's look at some of the other values for the thermistor, and we'll end the video.
On the upper left, the thermistor connector is circled in red. This is where you will plug in your thermistor attachment. On the lower right, on the main pin block, you'll notice that the div 2 pin is highlighted. Now on the V2.0 board, we will not be using the div 2 connection. We will actually be connecting the voltage divider from our thermistor to this pin, and it will be relabeled THRM. This is a temperature versus resistance chart for the thermistor. It is all of the resistances are in kilo ohms. For instance, on the upper left, negative 40 degrees Celsius. The thermistor will have a resistance of 340.9281 kilo ohms. So that's 340 and change thousand ohms. If you go to the polar extreme to 105 degrees on the lower right, you'll notice that it's actually less than a kilo ohm. It'll be 582 ohms roughly. So 0.5821 kilo ohms. Room temperature, we tried ourselves. We tried at roughly 20, we talked about 20 degrees. And at 20 degrees, you'll notice that the resistance of the thermistor is roughly 12.5005 k ohms. One more example would be 50 degrees C, 3.5893 kilo ohms. Now, I'll be including this in the manual, but you can always refer back to this specific video if you want to learn more about how the thermistor is working.